Hello and welcome to another episode of Twiml Talk, the podcast where I interview interesting people doing interesting things in machine learning and artificial intelligence. I'm your host, Sam Charrington. All right, Twiml listeners, this is your last chance to join the conversation and share your take on home and personal AI. Entries for our My AI contest close on Sunday, February 25th at 11:59 p.m. Eastern. So go ahead, hit pause right now, jump on over to twimlai.com/myai, check out some of the existing entries, and submit yours. Before we move on, I want to give a quick shout out and thanks to everyone who has submitted a video so far this week. So cheers to you, Matt, Bradley, Lawrence, and Mohit. In this episode, I speak with Sriraam Natarajan, Associate Professor in the Department of Computer Science at UT Dallas. While at NIPS a few months back, Sriram and I sat down to discuss his work on statistical relational artificial intelligence. StarAI is the combination of probabilistic and statistical machine learning techniques with relational databases. We cover systems learning on top of relational databases and making predictions with relational data, with quite a few examples from the healthcare field. Sriram and his collaborators have also developed BoostSRL, a gradient boosting based approach to learning different types of statistical relational models. We briefly touched on this, along with other implementation approaches. All right, let's do it. All right, everyone, I am here in Long Beach, California. I'd say sunny Long Beach, California, but it's actually fairly late in the evening. My first interview here at NIPS, in fact, the first time I've attended the NIPS conference, and I've got the pleasure of being seated with Sriraam Natarajan. Sriram is an associate professor of computer science at the University of Texas at Dallas. Sriram, welcome to This Week in Machine Learning and AI.
Hey, great to be here.
Why don't we get started by having you tell us a little bit about your background and how you got interested in machine learning and artificial intelligence?
So my interests are in machine learning, artificial intelligence, primarily in this field called Statistical Relational Artificial Intelligence, about which we are giving a tutorial tomorrow, which is why I'm here at NIPS. And the application and adaptation of these algorithms to many real problems, focusing mainly on healthcare type problems, but also on natural language, understanding, finance types of problems, but mainly focusing on healthcare problems. How did I get interested? I think it started from my grad school. When I came here for master's at Oregon State, my interest was primarily just computer science, in the broad area of computer science.
Okay.
But I took artificial intelligence courses under Professor Prasad Tadepalli, who went on to later become my PhD advisor.
Okay.
And I don't know, I just liked the style of teaching. I like the fact that the artificial intelligence and machine learning techniques combined two of my favorite topics, math and statistics, with computer science.
Okay.
So the combination of math and computer science kind of lured me into AI.
Nice.
So my thesis was primarily in artificial intelligence and machine learning.
Okay.
Didn't have too much healthcare problems. When I did a postdoc at University of Wisconsin-Madison, Professor David Page and Professor Jude Shavlik introduced me to the possibility of using machine learning and artificial intelligence to solve healthcare problems. We are looking at electronic health data, electronic health record data from Marshfield, Wisconsin. That got me interested into kind of like personalized medicine. Now it's called precision health.
Right.
So I got interested in adapting our algorithms for these problems. So I think that's how my journey has happened so far.
Okay, great. And so you mentioned that you're doing a tutorial tomorrow, right?
Yes.
And it's on statistical relational artificial intelligence, right, or StarAI, yes, which is a great acronym.
Thanks.
What is StarAI?
So StarAI is the combination of probabilistic or classical statistical machine learning with more logical or relational artificial intelligence. The idea being that this traditional artificial intelligence techniques and machine learning techniques make a lot of assumptions on the data. They need a lot of pre-processing. They need a lot of engineering. Whereas what the StarAI methods try and do is kind of look at the data in a kind of a more holistic manner. Look at the data in the natural form, in the relational form. So a classic example is most of these machine learning algorithms do what is called as an IID assumption.
What?
IID, independent and identically distributed,
right.
Which means each of us is described by the same features or same set of attributes,
right.
And each of us is drawn independent of each other. And then you learn a classifier, you learn a predictor on top of us. Whereas if you look at real data, it's not true. The probability of you having diabetes or me having diabetes depends on your parents, and in my case, my parents, and my parents' parents, and so on. So the family history matters.
So I can see that's particularly not true in the case of diabetes or disease. Are there other examples outside of the healthcare realm where that assumption falls down?
Even social behavior, right? How even some small thing like the probability of somebody smoking depends on the fact that their social network friend smokes or not. How popular a particular person is, let's say in a scientific field, depends on who his or her co-authors, his collaborators are. So how the popularity levels of the collaborators. So if you take classical machine learning methods, they kind of project these multi-relational data into a single fixed flat form, and they operate on that. Statistical relational learning methods, on the other hand, allow the data to be in its natural form, and we try to learn using the power of first order logic and relational logic. So think of learning in a relational database using statistical methods. So that's why it's called statistical relational artificial intelligence, because it takes the classical machine learning methods but kind of upgrade them to learn on relational data, allowing data to be in the natural form. So you take any data, electronic health records are classic examples, but you look at social networks, or you look at author citations, you look at movie databases, everything, most real data. Now Google stores, everybody stores the data in a relational database. But somehow when we are learning it, they are transformed into a different format. And they are aggregated, they are somehow shortened, and they are all compressed into one form, and then the algorithms run on those compressed form. In our case, what we're saying is, well, let the data be in its pure form, which is relational. Somehow let the models be learned at a relational level, which is why we sometimes call these models as lifted models, because they are lifted from a flat representation to a much more richer representation.
Now, when you first started going through this, the first thought that jumped out in my mind was relational database. But then as you described it from the context of, different distributions and kind of moving beyond the independent, identically distributed assumption, I thought, he's not talking about relational database stuff. But then you come back full circle to relational database. Can you elaborate on the relationship between statistical relational AI and relational databases?
So relational databases are representations. So relational databases are how the data is actually stored on whatever you're storing them on. The statistical relational AI says, I'll take the structure of the relational database and learn a model upon the structure. So what happens is, so let's just take a simple example. In an IID framework, in the classical machine learning framework, each of us, you and I, your father, my father, we all become individual examples for a classifier. Okay. In these relational models, however, your family becomes one mega example. My family becomes one mega example. We may be connected, I don't know, by when we go like 20 levels up, but for whatever data we have, we could be different sets of mega examples, and we are. So what the statistical relational learning does is learn at these mega example levels than at individual example levels. So how are they related to databases? If you look at a database and I start, let's say with you, or let's say we start from Sriram, that's easier to explain in an academic context. Then you go to my advisor, maybe my advisor's collaborators, my collaborators. You can form a small network of people around me and basically use that information to predict something about me, whether I'll be successful, whether I'm going to have a paper next year, or whether I'm going to have a grant next year. You may be able to predict that by looking at whom I'm working with, what topics I'm working on, how popular it is, and so on and so forth. When it comes to relational data, you're basically looking at all the relations that are connected to me and figuring out how you can make some predictions about me. This is true not just in citations, it's true in many of these health care problems, it's true in natural language problems, it's true in any real problem that you look at. You have objects. People are objects and they are related, and you have objects everywhere, right? People are objects, things are objects, and emails are objects, and projects are objects, and then we are all related to emails and projects and papers, and so on and so forth. And then you start talking about relations. How are these relations? Maybe two people work on a project, right? There's two people work for another person, and that person reports to an organization, and the organization is managed by somebody. So there's always these rich relations that you can tease out from a database. So it's very related to a database, and you can think of what we do as learning on top of a database.
So I'm envisioning then, well, I guess there's two directions that I want to go with this. One is the extent to which what you're specifically talking about is from an implementation, related to learning on databases, meaning, taking advantage of, schemas and primary keys and things like that. That's kind of one possibility. But then I'm also hearing something that sounds to me like, whereas we, might have in traditional machine learning a set of independent examples, in statistical relational AI, you've got, this set of examples and kind of overlaid by some connectivity graph. And it sounds like what you're, what you're doing in a sense is maybe, finding different ways to kind of featureize that graph and use it in the training process?
Yeah, that's actually one reasonably simple way of understanding what we are doing.
Reasonably simple is a great place to start.
That's true. The reason I'm saying reasonably simple is because we really do not construct too many features. We let the features be defined based on the relationships themselves. So for instance, let's go back and take a classic example of movies. Okay, I want to predict that the next Marvel movie, how much money is it going to make? And then you want to look at, well, typically people look at history, how things change and so on, but you could also look at the actors, and you could look at the different actors that are involved in a movie. And you could say, well, these lead actors have typically tend to get a lot of box office collection and so on and so forth. So what we are trying to do is we are looking at the fact that one Marvel movie might have 5 stars, five big entertainment stars, like big actors, whatever. And then another movie, on the other hand, might be carried solo by a single, Iron Man. Is Iron Man even Marvel, or are they DC?
That's Marvel.
Okay, I got that right. So, Robert Downey himself carries one movie with him. But let's say the Avengers or some other one is carried by 5-6 people. Does that necessarily mean that it's better than one? We don't know that, right? And what typical machine learning methods tend to do is kind of collapse them into one group. We, on the other hand, say, well, how about we let the data speak for itself? Maybe each of them combine some way, and I look at the previous Avengers, look at who's directing, who's imparting. So from that perspective, I'm not doing too much feature engineering, but I'm figuring out how can I use this graph of people and use that to make a prediction that I cannot with a normal machine learning algorithm. The other problem is, here is the problem, okay? So let's say you in classical machine learning, you make an assumption. Oh, I'm going to look at the top 5 actors. But let's say suddenly Marvel decides to make this mega Avengers movie with 20 actors. Okay, so you got to go back to your model and say, oh man, we went from 5 to 20. And you have to adjust your model.
Apply in this world?
You might want to, you cannot generalize that easily. We, on the other hand, make no assumption on the number of individuals, number of objects. We can say, as long as, they are actors in a movie, we're going to use their information to make predictions. So that's where the power of relational representations come in. And they're kind of tied. Actually, you asked me 2 questions. One is on the implementation aspect, and I don't think they are too different. Because when you think about how these are ultimately implemented, they are in some sense implemented based on either a logical representation, the power of first order logic, as people know for a long time in computer science, or from a relational representation as a database. So which is why in US this is called statistical relational learning, because most of the work is done on top of relational databases. In Europe, This is called probabilistic logic learning because most of the machinery underlying is a logical representation. And both of them do minimal feature construction.
Okay.
They kind of learn at the level of the databases. The cool thing is they are statistical and probabilistic because you can allow the data to be noisy. So that's what happens. So our data can be noisy. Our models are robust to noise. Our models are robust to changing number of individuals, number of parameters, number of objects in the world. And so we learn at the level of objects and relations, not at the level of specific people.
Okay.
And I think that's why these models are powerful.
Okay. And so how does it work?
How does learning work, or how does...
kind of what's the method that you apply to
So
do
what
this?
we do, for instance, I'm going to talk about one specific method that we do, which is called relational functional gradient boosting.
Okay.
There is this famous gradient boosting technique inside machine learning. What we are doing is we are elevating it to the relational setting. So it's called lifted gradient boosting. And the idea is very simple. So let's say I'm interested, let's just take a simple example. I'm interested in predicting if somebody has a heart attack, okay? And we look at the database. Let's say I'm a positive example in that I have a heart attack. Sam, you're a negative example. You look much fitter than I am, so you don't have a heart attack. What happens is my model uses my attributes and it starts to learn. And then it says, is the father of this person diabetic? Turns out my father is, okay? And then is the cholesterol level of this person pretty high? If so, then the probability of a heart attack is, let's say, my model comes up with me having a probability of 0.7 as a heart attack. The same model comes with you to have a probability of 0.13, okay? Now because I'm a positive example, it should say that I have a probability of 1 to have a heart attack, but I said 0.7, which means 1 minus 0.7, 0.3 is the mistake that the model makes on me. Your probability should have been 0 because you don't have a heart attack according to the data.
Right.
But my model said 0.13 as your probability. So your weight, so to say, is minus 0.13. That is the mistake. So every positive example will have a weight of greater than or equal to 0. Every negative example, like you, will have a weight of less than or equal to 0. So what we do is we learn a small model, regression model. It could be a class which says if the father of this person is diabetic, and if this person's cholesterol level in the last 3 months is greater than, I don't know, if let's say the HDL cholesterol is less than 30, then the probability of heart attack is this. You could go do other things, for instance, that says the relational power comes from the fact that your class could say something like, if any of his close family members, and this close family members could mean my dad, my dad's dad, my dad's brother, my mom's brothers, and so on and so forth. And you will have completely different number of uncles and aunts as I do. Okay, so you could say something like, if a close family member has a predisposition for heart attack, then the probability of heart attack for me is so much. And you could say that because of the fact that I'm not defining, I can define close family member to be either an uncle or an aunt or a first cousin or, my grandparents on either side and so on and so forth. And we are not restricting the number. You just look into the data and you can learn it. So what the model does is it tries to find out these factors that matter, put them together and make a prediction. And then it finds which mistake, where it makes a mistake, learns something else to fix that mistake. So for people who don't have low HDL and whose father don't have let's say diabetes, they could be that they smoke a lot and drink a lot. And for them, there is a different issue. So what the model does is, okay, I've got Sriram mostly covered. There's only a small mistake on Sriram, but there is this other person who has a heart attack whom I have not covered. So let me focus on that person. So it kind of fixes these mistakes repeatedly and learns one robust model in the end. And it scales up pretty well. We have the code is available online, so people can look at that from my webpage as well.
Okay. A couple things. So one, you talked about heart attack, smoking, cholesterol levels. These are all things that I would associate as being features in a traditional model, but yet you said that you don't really get into features as much with this. How do you reconcile that?
So I have to make it clearer in the sense that these are all features. So everything is a feature.
Okay.
What I'm saying is we don't really do a lot of feature engineering.
Right.
We don't say, for instance, beautiful question, right? So let's say you go to the hospital. Again, you're looking much fitter than I am. You go to the hospital maybe once a year to do your annual checkup. I go to the hospital 3 or 4 times a year. Okay. Now think about how a classical machine learning algorithm will do. You will have one measurement of cholesterol. I will have 4 measurements of cholesterol. I might have my A1Cs recorded every actually 4 is good for a year. So 4 A1Cs, which is every 3 months, I'm going to record my blood sugar level. And so I have multiple measurements and you have only one measurement. How do we do this? Well, classical methods say min, max, average. So it takes an average of my cholesterol level, it takes a minimum, maximum, and puts them as features. This is what we call as feature engineering.
Right.
Okay? We don't do that. We say, if the cholesterol level in the last 1 year has ever been greater than this, and that can be written by logic. So a logic statement says there exists a cholesterol level. This is called quantification in logic. And so they so we don't even do that, min, max, etc. They can be done. If needed, we can do it. But doing that is a subset of what we can do. We can just let the data as it is, which says that anytime in the last 5 years, Sriram's cholesterol level has been this. Anytime after the age of 55, this person's A1C has been this. And so we can tease that out. So what I mean by feature engineering is we don't construct specific features for specific problems. You just let the data be in its natural form.
That still sounds like feature. It sounds like the if statement is like a one-hot encoding on whether their cholesterol has been high.
So cholesterol is a classic example. Okay, cholesterol might not be the best example to illustrate the difference.
Okay.
Take the smoking properties of a friend. Okay.
Right.
If your close friend smokes, the probability of you having a heart attack is 0.3 or 0.4. How do you define that in a propositional or in a normal setting?
Okay.
I want to say if a close friend smokes.
Features fall down because they're not related to the individual entity.
Exactly.
Whereas you've got this broad universe that's captured by all these relationships and it's all features, but they're not like features of me. It's features of this network.
It's features of this network and the size of the network varies between people.
Right.
So in the end, everything is a feature. You're right.
Right.
But what is a feature of? My point is that we don't do specific feature engineering continuously. We let the data in its natural form, which is, I could talk about objects and relations and features of those objects and features of those relations.
Right. Okay.
I just have to say, well, again, you might have 5 close friends. I might have 3 close friends. How do you encode this?
Right.
Right. Whereas our models can just handle them because it just says, is there one friend? Is there 2 friends? You can just look at it and you can learn from it. It's easy to do that.
I thought you were going someplace that you didn't end up going. It strikes me that you gave the example of the multiple. You go into the hospital multiple times a year and get your 4 A1C readings. I go in once and get my 1. And then you write your rule that basically looks to see if I have been, have had a higher A1C reading over the past N years.
Yeah.
It strikes me that you've kind of lost a lot of information. Maybe there's information in the fact that you actually went 4 times and I only went once.
That's a great point. It's not necessarily that we lose that information.
Okay.
If you want to take that, you can record that too. Okay. So actually, 2 things that I want to clarify. First, I don't write the rules. Because of this boosting algorithm, rules are automatically learned from data. So we use only data and we use some domain knowledge. Actually, I work on what is called as knowledge-based machine learning. Okay. Now we call it as human-in-the-loop machine learung. So there is a human expert. We work with cardiologists, we work with radiologists, we work with neuroradiologists, and so on and so forth. We have a lot of collaborations in medical with medical groups.
Okay. And so did they write the rules or are the rules learned by algorithms?
The rules are learned by algorithms.
Okay.
What they give us is a little bit more knowledge. Okay. They can say things like, this guy is much more difficult to predict than this person. And then we tell the data, focus on this person. Or a person could come and say, I'll come to that about the experts in a little bit after I answer this question. Okay. So we don't provide the rules. The rules are learned automatically from the data. Okay. And the rules themselves are capable of learning that. The rules themselves are capable of saying, if the number of visits matter, then it can say actually, if the number of visits is greater than 4, and in that number, if there is A1C reading greater than this much.
So when you say you don't learn the rules, does that mean you don't learn?
No, we don't write the rules.
Right. Sorry.
We learn the rules.
When you say you learn the rules, are you learning the parameters of the rules,
No,
or are
we
you
learn
learning
the
the rules themselves?
We learn the rules themselves along with the parameters.
Okay.
Which is why, so if you think of like a complex neural network or a deep network where I'm writing these features out, the features themselves can be learned by us.
Right.
So we learn these rules, which are basically if-then-else. Think of them as if-then-else statements.
Yeah.
And then we parameterize them with probabilities or real numbers, depending on whatever interpretation you take. But we learn the rules from data. So we learn it from data.
Okay.
Now going back to the other point that that I wanted to make about experts. Experts can provide a lot of things. Experts can tell us things like, in some cases, false positives are more important than false negatives. Okay. So, for instance, in recommendation systems, I'm recommending a job to you, right? Or I get these LinkedIn recommendations which keep telling me there is a postdoc position open, right?
Okay.
And I'm like, come on, man, I did my time. That was 7 years back. I don't want to do this again, right? So that is a false positive. It's a false positive. There, from a recommendation system perspective, that needs to be eliminated. If you tell me 4 jobs, only 4 jobs, and those are all relevant to what I'm looking at, I'm going to trust your system. So out of the potentially 4,000 jobs, you may list only 4 jobs, but those are important to me, so I'll look at it. But if you give me 20 jobs, out of which only 4 are relevant, the rest are all false positives, then I'm going to lose trust in your system. Now think exactly the opposite side of an epidemic. You're interested in predicting Ebola, for instance, right? It's okay to quarantine 4 more people. What is the worst thing they're going to do? They're going to sue the city. $1 million each. At most $10 million is what we're going to lose. But think about releasing 4 people with Ebola into the general community. Then it becomes an epidemic and costs us billions of dollars, just to talk in terms of numbers. So what I'm trying to illustrate here is, in one case of recommendation system, false positives are more important than false negatives. In another case, false negatives are much more dangerous than false positives. An expert could come and tell us, ooh, no, this is the case where this is more important than the other one.
Okay.
And what we do is we think of it as a knob and turn this knob on the classifier and say, oh, you know what, that's what it is. And in another example, a domain expert could say, Sriram, for people, what I have observed in my experience is that for people with high cholesterol, if they have high BMI, then the risk of a heart attack is higher than people with lower cholesterol. So even people with high BMI have 2 different effects. They are not exactly telling me how these things influence, except they give a qualitative understanding between 2 things and a target of heart attack. So that's called monotonicity, synergies. They call qualitative relationships. We can take that. You can take preferences.
And how do you encode that kind of thing?
I'll come to that in a second. I'll just illustrate this one thing and I'll come to that. So third thing, for instance, is I was in a college town, Bloomington, Indiana. Let's assume that you're trying to build a robot, and the robot is sitting on top of a building, having a donut in one hand and observing how people stop at stop signs. I'm in a university town, which means only 50% of the people stop at stop signs, right? and then the machine could ask the human, hey, I'm looking at this data, but like only 50% seem to be stopping. What do you think I should do? Then the expert could say, well, I prefer that you stop at stop signs if it is safe to stop. Maybe there is an extreme case where, you don't want to stop in a stop sign because it's dangerous actually to stop, right? You might put you in danger or somebody in danger. I don't know. I can imagine such situations with autonomous cars, for instance. And you say something soft that says, I prefer that you stop in stop signs. And then it says, okay, great. Then what our algorithm does is it takes these statements as constraints. And then it combines that with the data that I have. Okay, so there could be regions in the data where there is a lot of mistakes, like stop signs. Then it says, ooh, the data has a lot of mistakes, but the expert has told me that this is what he or she prefers. So what I'm going to do is take what he or she tells me, combine it with my data, and wherever the data conflicts the expert or the expert conflicts the data, I'm going to weigh that lower. Wherever they agree, I'm going to weigh that higher and kind of incorporate that into my model. So what I do is I get these human inputs as constraints to the learning algorithm. And we have shown across several publications that such constraints improve performance. And very recently what we have been trying to do is also do a little bit more, which is let the algorithm ask questions.
Okay.
Instead of the expert telling. So when we started this research, the expert has to say everything that he or she knows about the problem. And then we take them as constraints and learn. But now we have gone the other way and we have said, we'll start looking at the data in the regions where we have extreme uncertainty about things that we are trying to learn. We will solicit information from the expert. So we call it actively seeking advice.
Okay.
So the key is for the machine to know what it knows and solicit information about what it does not know. And the expert could say something, it takes that back into the model, adjust it. Again, because it's an iterative learning method that we have, it can go back and try and fix its mistakes.
So let's put this on the stack after the answer to the encoding question.
Okay.
But it strikes me there that there's a huge gap between what the algorithm is likely to surface. Some factor is, there's a high degree of ambiguity in some factor, and something that you can present to a doctor that, makes that intelligible and kind of elicits useful advice to feed back into the algorithm, which goes back to the encoding question. Like, how does all that part work?
Beautiful question. That is a fantastic question. And that is another reason why these logical models are more useful.
Okay.
Here is the problem. If I now use a very complex learning system underneath, then it's going to say feature 176354221.
Right.
Seems very weird for me. And I go to the doctor. The doctor is not going to know anything, right?
Right.
On the other hand, mine is a logical clause. It's an if-then-else statement. So it could say, for people who have slightly lower HDL level, but on the other hand, their triglyceride level seems to be good, there seems to be a lot of distribution over these heart attacks and diabetes. What do I do? So what happens is, because of the fact that we are learning these knowledge at the level of the data themselves, the relational schema themselves, it's easier to present to the doctor because they know what the schema looks like. It's not just the doctors. We work again with financial experts. So again, our legal experts. So we have these documents and we can say, well, you can't say something like if the parse tree comes up with this noun phrase. No, but we can extract the that says this part of the sentence that seems to be always conflicted with this part of the sentence. Why is that? And we can ask that question. And that is only because of the fact that we are learning a much more representative model, a much more interpretable model than a typical complex model learners. So that's because of the fact that you're learning if objects type, objects value, objects relations are like this, then something, right?
Okay.
So then you can present this to the user. So that's another power that comes from these relational models that you don't get with standard models. Yeah. So
can you talk a little bit about how you benchmark this relative to other approaches and what kind of results you've seen?
So that's something that we do all the time extensively. What we try and do is we take these models and try to, so for instance, if I have to run a deep belief network or something, we try to create, as we spend a lot of time engineering as much as possible. And try to engineer this a lot and then create many features, and you try to use a standard machine learning algorithm as your baseline. Now what happens is, for the current data set, it might learn a good performance, right? On your training set, it could actually give pretty good performance, because most of these machine learning algorithms can learn well if you engineer your features very well, and that's doable. We do that.
Right.
The real problem comes when it comes to generalization. So most of the benchmarking that we do is on generalization. So for instance, you learn about whether a student works with a professor from one university, right? You test on that university, most of these algorithm works great. Now what you do is you go to a different university and deploy this model.
Right.
And they kind of break down because you have to create new features, new things. Whereas these relational learning algorithms, because of the fact that they learn not at the level of the individual professors, but at the level of these groups of people, the sets of people, it's much more easy to adapt and transfer.
Okay.
So when we do this benchmarking, we try to figure out, let's say, other networks, which is why a classic example is, let's say you've used all of Sriram's family network data. What I'll do is, when I'm testing it, I go to Sam's data and I see, does Sam's data work on my model? And then you do that with these classical methods. Some of the times you don't get them. Sometimes, if you know what you're going to test on, you can certainly engineer and try and do that. But most of the times, these relational models work beautifully on those problems as well.
Yeah, I hear people talk all the time about like overfitting on ImageNet and things like that in the industry, in the field. Do you feel that this notion of kind of focusing on generalization as opposed to performance is like underappreciated or under pursued in this space?
Definitely. But the good thing is that there's been a new conscience on looking at generalization as an important aspect. But initially, there's been a lot of work on the science of experimental methodology of machine learning. There's been a lot of work on empirical machine learning. I think that's an extremely important research direction.
Right.
People kind of lost a little bit of that oversight when we went and developed aggressively more and more newer models. But I think now people have started realizing that because of this abundance of data sources, and we have these multiple data sources that we have to somehow integrate and work with, suddenly generalization again has become an important issue. So I from my limited 15-16 year experience, I have seen that there is a lot of interest now in making sure that we build models that generalize across populations, across data sets, across diverse data sources. And I think that's certainly an important research direction. And which is one of the reasons we want to make sure that any model that you develop is not tied to that particular thing. And which is why when I see many of these people talk about AI, we're all a little bit worried because it is such a specific, domain-specific solution that you are always worried when it's going to break. And it could break very easily if you don't think about generalization.
Are there standard and well-accepted ways of measuring generalization, or do you feel like everyone kind of figures it out, presents their own results in their own way in papers?
There's a lot of work on generalization errors and understanding generalization errors. Cross-validation and the whole bias variance theory has tried to figure out how the bias on a particular data set is going to affect the variance across multiple data sets. So there's definitely a lot of understanding in statistical machine learning on this notion of generalization error. And people have definitely looked at it. But I think when it comes to the practical implementation, people tend to ignore it. They tend to kind of evaluate them in a very narrow field. I've even had students, both in my class and in my research group, sometimes build these so-called tuning sets where you fix your parameters using this tuning set for your learning algorithm from test sets. You should never do that. That's like cheating. That's like having a practice question from the final midterm or the final exam that you have. You're going to have a practice question on that. So that's cheating. But students do that all the time. So we tend to try and teach them that's not the right way to do it, and we try to show them a proper way to do it. So there's definitely a lot of work on generalization and understanding generalization. But remember, it's within a certain domain. Can we do it across domains? Maybe, maybe not. Like, can you take something like learning how to drive a car and figure out how to drive a plane or fly a plane? No. But maybe driving a car in US versus India, I can't imagine doing that easily, but you could do that. You could try and understand how does it generalize across multiple countries, and trying to understand how the rules of the domains change.
At some point, it gets into just artificial general intelligence, right? It's like if you can generalize across every domain, that's the goal. That's a goal.
That's a goal, but I don't know. I mean, I'm not saying that you need something that is very general. I'm saying that you need something that is generalizable enough inside the same problem domain at least.
I think we understand.
So if I build a model, as I said, for driving in US, that should be able to drive in Europe, if not in India, let's say. That level of chaos may be difficult, but maybe at least in Europe, maybe in London, it should be able to drive a car if I teach it how to drive a car in LA. And that amount of generalization should be there at the very least. Would be cool to drive a car in India. That would be awesome to achieve it. But I'm not really looking for this one system that drives and flies at the same time. In fact, I'm worried that might lose some specific knowledge that a driving agent will have that the flying agent will not. So that's the balance. How much general knowledge do you want, and how much specific, I guess, what's the right word here? Specific skill set you want for solving that problem. I think that's the difference that that we have to find. And the sweet spot depends on the problem domain. In some problems, so think about it. Like you have a problem and you go to a doctor, and this doctor is a neurologist. Okay, and now you want to talk a little bit about diabetes. This person is going to tell you something, but they're going to say, "This is what I know, and you better talk to somebody who knows this better."
Right.
And you go there, right? Or like a cancer, right? You want to go to an oncologist, right? And but before that, you have a family friend who's a radiologist. The radiologist is going to give you a lot of information,
right?
But then you say, but I'll still refer you to this oncologist for your treatment plans.
Yeah.
And that's what you want even with systems. You don't really want systems that says, "Oh, I can solve this and this and that and this."
Right.
And so not too generalizable, but so artificial general intelligence is great, but we also have to accept that that comes at a cost.
It's contextual.
Yes,
in a sense.
Exactly.
You mentioned you had code up on your site. Tell me a little bit about the code. Is it kind of code applied to the healthcare set?
So that's a great question.
General algorithm, or
it's a general algorithm. It's a boosting algorithm that anybody can download. It's a gradient boosting, but operates on relational databases.
Okay.
We have an extensive tutorial on how to convert your data to R format, how to run the code. We can learn multiple types of models, relational probabilistic models. We can learn multiple. We can take the human inputs on this. We actually have a wrapper that can do natural language extractions. So you have text data, but you want to, let's say, figure out who is married to whom based on paragraphs, reading some CNN articles or something.
Okay.
And you can post that problem. We have shown how to do it. So there's an extensive tutorial on how to use this. Okay. It's available off of my webpage.
Okay.
If you go to my lab webpage through my webpage, in the software, it's there, and people can download it and use it. It's a general purpose software, not only applied to health problems.
Okay.
When it comes to health problems, there is always a catch. We have to be very careful on what we release and what we don't, and so on and so forth. So yeah.
Okay. And then we've been talking about relational databases, but there's a whole type of database called graph databases.
Yes.
Does your method apply to graph databases as well?
Fantastic question. Yes. The answer is yes, because graph is a relation for us. Right? Nodes and edges are relations. So relation is this common word that we use.
Yeah.
So graphs are just relations. And actually, because one of the most important steps inside our optimization function is to count. You have to count the number of instances. So count the number of papers that somebody wrote, count the number of friends that somebody has in Facebook, and so on and so forth. And that counting is actually a complex problem. So we actually use graph databases to accelerate our counts.
Oh, okay.
So we do use sometimes a intermediate representation of a graph database to accelerate our learning. So for us, graph databases and databases, graphs, they're all structured problems that we can handle using the formalism of logic. Absolutely. So the answer is yes. And what we are trying to do is actually do exactly that. Build a version that is more optimized for graph databases, because graph databases are much simpler sometimes than the full logic, like Sci-Corp knowledge base or never-ending language learner, NEL knowledge base. Those are logical knowledge bases, and those are huge. Whereas a graph database,
what are they called again?
Sci-Corp.
Sci-Corp?
Yeah, Sci-Corp is this company that's been running that's been building a knowledge base for over 35-40 years.
Okay.
And so those are like giant knowledge bases.
Okay.
Whereas graph databases are much easier to manage and work with. So they may be even faster for us to learn with. So yeah, absolutely. Learning with graph database is something that we do all the time.
Okay. And so you're out doing the tutorial, kind of evangelizing this approach. What's the end goal for you? Are you trying to get grad students and postdocs? Are you trying to get industry to adopt this? What's the motivation and vision?
I think we want people to be aware of this big goal of statistical relational AI. We want people to know that deep learning is not everything, and we want people to know that there are other learning areas that focus on some richer, probably more important questions. Turns out that the four of us who are giving the tutorial actually have large groups ourselves, so it's not like we are trying to recruit people here, but we are going one conference at a time to kind of show that this field is now actually much more matured than what it was 10 years back. And we are trying to tell people that there is a lot of opportunities inside our field. So combining deep models with logical models combining, let's say, matrix factorization with relational data. So there's a lot of opportunities for this. And that's what we are highlighting in the tutorial tomorrow, is inviting more people to work on similar problems like we do. And that's the ultimate goal for us, is kind of show people that this is an important research area and problem, and that all of us together can contribute to. So we want more people to work on these problems. I think that's our end goal.
Great. Are there specific examples of like case studies or like, health centers or products that use this, or
yeah, that's a very good question. So I think one of the case is this deep dive by Professor Kirisre from Stanford.
Okay.
That's now been bought out by Apple.
Okay.
So this is this probabilistic databases, which kind of is statistical relational AI in some sense, that automatically extracted information, knowledge extraction from videos and images and text. And so that's a classic case. We have been working with hospitals on trying to see how we can put the data back into their learning system for making predictions on the number of hospital readmissions, the number of procedures that need to be done on some persons.
Right.
We recently have got some very good success on using such models on predicting postpartum depression by looking at the network of women, network of people that the women are in touch with. And so we are trying to talk to people to see how this can go out to the market. We work with a particular bank on looking at their legal documents and figuring out if a new document comes in, does this match the standards of the company, of the bank? And we can do that automatically with like 98%, 99% accuracy.
Oh, wow.
And the ones that we fail, we can flag it and show it to the human expert who currently currently looks at it. So yes, there's a lot of these case studies out there. But again, we are trying to do the deployment at this point. So maybe hopefully if I talk to you in 2 years, I'll be able to say, well, I probably will not be able to say company A uses it, but I can say there is a company that uses it. Same thing with recommendation systems. The job recommendation system is actually a real project that we have done with a real company, and they are looking to use our product in their collaborative filtering system. So yeah, so there's a lot of success stories on this, actually, which is what we're going to highlight tomorrow. You should drop by.
Yeah. Awesome. Well, Sriram, thanks so much for joining me. I really appreciate having an opportunity to learn about statistical relational AI.
Thank you.
Any final words or places that you'd like to point folks to, or anything else?
Oh, thanks. There is a book on statistical relational AI, of course, that I'm a co-author of. Actually, the 4 of us who wrote the book are the 4 who are giving tutorials tomorrow.
Okay, wow.
And there's a series of workshops that happen every year that the 4 of us, again, founded 9 years back. I don't know. It's 8-9 years back. I'm getting old. But now people are running it. It's kind of self-sustaining in its own. So I invite people to look at these problems of statistical relational AI and contact any of us if you need any directions or anything of that sort. I'm very, very happy to help.
Awesome. Thanks so much, Sriram.
Thank you. Thanks.
All right, everyone. That's our show for today. For more information on Sriram or any of the topics covered in this episode, head on over to twimlai.com/talk/113. Definitely remember to submit your thoughts on AI in your life at twimlai.com/myai. And of course, thanks so much for listening, and catch you next time.